All right, so 5.4, we're going to be talking about conditional probabilities and the general multiplication rule. So in 5.3, we dealt with independence, where two events did not impact each other. This lesson, when we're talking about conditional probabilities, that means the first event in a series of events impacts the rest of the events. So we started in 5.3 talking about taking a card out and then putting it back in the deck and then drawing another one. That's independent because you're putting that card back, you're resetting the deck so that all the cards are there. In 5.4, when we talk about things like taking a card out of a deck, we are no longer replacing it. We have pulled that card, we've kept it out, and so now we've changed the odds for that next card picked. And so that second draw is conditional based on that first one. So your chances of getting the ace of spades on your second draw depends on if you pick the ace of spades on your first draw. You can't get it twice. So when we talk about conditional probabilities, we're talking about events that are related to each other and impact each other. So when we're using conditional probabilities, we use P of B bar A. So B and then bar and then the A. And so it's pronounced the probability of B given A. So that little line represents given. So this guy right here is our given. B given A. And there's going to be a couple different ways we find that. First, we're going to talk about two-way tables and how we can use two-way tables to do that. Then we're going to talk about using this formula where we have the probabilities. And then finally, we're going to talk about kind of an intuitive way of doing it when we deal with like decks of cards and stuff like that. But that's how we're going to be looking at this, is in two different ways. One, given the actual numbers, given the two-way table, given the sample size and stuff like that. And then we're also going to talk at using just the probabilities and how to read those probabilities and figure that out. And if the probability in A and B don't overlap, you cannot multiply. So you have to be very careful when we're talking about conditional probabilities. The A and B refers to the overlap of the two events. You do not multiply those two things together. We can only multiply those two things together if they're not related to each other. And in this entire section, we're claiming that they are related to each other. And so we can't multiply. So remember this, do not multiply. We're referring to the overlap of things. So be careful with that. That's a common mistake. All right, so going back, we dealt with this table earlier when we did our two-way tables of ands and ors. Now we're going to be looking at conditional probabilities. And the way we do that using two-way tables is by changing the denominator. So in 5.2, we looked at different things, and we used that 137,243 as the denominator all time. This time we're only looking at a subgroup of this table. So let's take a look at what I'm talking about. What is the probability he died from cancer given he was a former smoker? So died of cancer is A, former smoker B. So let's go through and look at how we have this. Which of those two things is given to us? Do we know for a fact that he died from cancer, or do we know for a fact that he was a former smoker? The fact that it says given he was a former smoker means that we know that for a fact. So remember that bar is the given part. So we're trying to find the probability of something given the fact that he was a former smoker, and the probability we're trying to find is A. So we know for a fact he was a former smoker, which means the only thing I'm only looking at that group of numbers, because those are the only numbers that involve former smokers. So how many people died of cancer? So we have 91 people over the total former smokers, 78-48. And so that's how it differs between the way we were using a two-way table with our ands or with our ors before, we're adding everything together. And now with the conditional probabilities, we're not looking at the entire group, we're looking at a subset based on that given piece of information. So now let's take a look. Given someone died of cancer, what is the probability? Current cigar smoker. So again, in this case, we're given A. We're given that someone died of cancer, and we're trying to find the probability that they were a current cigar smoker. So again, we're looking down. This time, I'm only looking at these numbers because those are the only people that fall into my given category. And inside of that given category, I'm looking for those people. And so again, I set up my probabilities, 141 over 1014. And when I have that, calculate the probability, 0.139. So again, the trick when using or trying to find conditional probabilities, if you're given a two-way table, is to make sure that you're limiting the sample space you're looking at. You are not looking at everyone when you have a given piece of information. You're using that given piece of information to shrink down and look at a subset of the entire table. All right, Brett is going to college. The table includes information on possible roommates. Find the probability that Brett's roommate will be someone who likes to party given that he snores. So again, let's take a look at this and say, okay, let's say so we have our two events, A and B. A is likes to party, B is snores. So first let's set up our probability statement. Our probability statement is that P, this thing here, that is a probability statement once we fill it in. So which piece of that is given? Do we know that he likes to party or do we know that he snores? So given that he snores, so we know that B is given and we're trying to find the probability of A. So probability of A given B. Again, since it's given that he snores, we are only looking at that column. And how many people in that column party? There's 150 out of the 300 people, which gives us 3/7 or 0.4286. All right, next we're going to go the other direction. I guess not the other direction, but we're going to use that formula now. So instead of having the two-way table and being able to look at the numbers, we're going to use the formula that says probability of B given A is equal to the probability of A and B divided by the probability of A. So that's the formula we're going to use, and so we need to try and find out where each of those numbers comes from and what they are. So, reading this question, in 2007, 12.7% of all births were preterm. Also in 2007, 0.22% of all births resulted in a preterm baby who weighed 8 pounds 13 ounces or more. What is the probability that a randomly selected baby was preterm weighed more than 8 pounds 13 ounces? Sorry, what is the probability that given that a randomly selected baby was preterm that it weighed more? So let's go through and figure out our two different probabilities, our A and our B, and then which one is given. So it appears that our two different events are if the baby was preterm, and then if the baby weighed more than 8 pounds, 13 ounces plus. So those are the two different kind of conditions that we're looking at. And now which one of those is given to us? Given that a randomly selected baby was preterm. So that means our A is the piece of information that is given. All right, so in order to find probability of A given B, I need to find the probability of A and B and the probability of A. So how many births were preterm? 12.7%. And when we're dealing with statistics, make sure you always use decimals. We are never going to be using percents here. So that is the percentage of all births that were preterm. So that gives me my probability of A. .22% of all births resulted in a preterm baby who weighed more than. And so that is both A and B, because it's preterm babies that weighed more than that weight. So this gives us 0.0022. And so now we can plug that information in. Probability of A and B, 0.0022 divided by 0.127, which gives us 0.0173. Again, remember that your probability must be between 0 and 1. So if you get confused and you flipped those numbers, the reciprocal of that. So if we did 0.127 divided by 0.0022, that is greater than 1, which means it cannot happen. So anytime you're getting an answer and your answer is more than 1, you've done something incorrectly. So go back and check your work. All right, dependent events, that's what we talked about, where the second event is affected by the first event. Picking 2 cards as long as you keep one, being a lifeguard, getting a suntan, having high grades, getting a scholarship, all of those are conditional things. The first thing impacts the second thing. So having high grades increases your chance of getting a scholarship. The general multiplication rule. So if we're trying to find the probability of an and we have dependent events, then we use this formula here. So if our 2 events are independent of each other, we have the formula we talked about before, which was the probability of A times the probability of B. Now, since those 2 events are dependent on each other, we have to change that up. The second one is not just the probability of B, the second one is the probability of B given that A happened. You can think of this as almost like a directional thing. So in this case, it's A and then B. So we know that A happened. Now that we know A happened, what's the probability of B also happening? So a deck of cards is a really easy way of doing this, because you guys should have a deck of cards or understand what a deck of cards is constructed or how it's constructed. So if we're writing the probability statement for getting 3 jacks, that is probability of a jack, and then a jack, and then another jack. Now, since we're drawing the card without replacement, this becomes the probability of getting a jack times the probability of getting a jack given the first card was already a jack, times the probability of getting a jack given that we already had 2 jacks. And so that's how that probability statement is written. We have first card is a jack, second card is a jack knowing the first card was a jack, and then the third card was a jack knowing the first 2 cards were jacks. I should rewrite that so it looks better. There we go. These are not ends. They're that intersection or the and. So, first card is a jack. How many jacks are there in a deck? There are 4, and there are 52 cards. Now, I've drawn a card. That card was a jack. How many jacks do I have left? Well, if there were 4 and I took one, now there's only 3. But how many cards are left? Well, a jack was a card, so now there's only 51 cards. So now it's 3 out of 51. Lastly, I've taken 2 of those jacks, and so now it's 2 out of 50. Now you multiply all of those together. .00018. So you see the probability of getting a jack decreases every time I take a jack because I'm decreasing the number of jacks in my deck. All right, pause, go ahead, finish these last two problems here, and then unpause and check to see if you got the same answers I did. All right, so we went through and did the same thing. Same setup. For B, it was an ace, then a king given an ace, and then a queen given an ace and a king. In this case, my numerator didn't change because I was changing the type of card I was looking for. So the numerator remained 4 the entire time. However, my denominator still decreased because I was still taking cards out of the deck. For C, again, same process, but this time the numerator was larger because there's 13 clubs as opposed to just 4 of one type of card. There's 13 cards in a suit, but other than that, same process. All right, so we did this same setup in 13.3. We had the same 3 red, 2 blue, 5 white marbles. And when we were doing that, however, this time when we do it, we are no longer replacing them. So when it is picked, it is not replaced. So we still have 10 marbles, selecting 2 blue. Instead of just probability of blue times probability of blue, it is now probability of blue times probability of blue given blue. We are now decreasing the number of marbles each time. So 2 out of 10 times, well, there were only 2 and we took one of them. So there's only 1 blue marble left. And so we have 1 out of 9. Which gives us 1/45. Go ahead, do B, C, and D, and then come back, pause it, and then come back and check when you're done to see if you got the same answers. All right, so finishing up, B, same idea, probability of blue, then probability of white given blue. So again, our denominator is decreasing because we're taking a marble. However, the numerator doesn't decrease because I didn't take a white marble the first time, so there's still 5 white marbles. C, again, same idea, red, then a blue given a red. So 3/10 because there's 3 red, then 2/9 because there's still 2, but I took 1 marble away, so there's only 9. And then in part D, same idea, the numerators are all the full numbers, so 3, 2, and 5, because I haven't taken any of them. However, I have taken marbles away, so that denominator keeps decreasing from 10 to 9 to 8. All right, last part of 5.4. A person owns a collection of 30 CDs, of which 5 are country music. If 2 CDs are selected at random, find the probability that both are country music. So, going into this, setting it up kind of the same way, what's the probability that the first CD that the person selects is a country music CD? Well, there's 5 country CDs out of the 30. If he takes one, what's the probability the second one is also? Well, now there's only now there's only 4, and there's only 29 CDs total. So same concept as before, just different wording. And so we get our answer there. That is the end of 5.4.